Okay, so welcome back. Let's start out by talking about an example of a set where there is a choice function. Okay. So first of all, let's say first we have a proposition. Let X be a finite set. Then X has a choice function. Okay, and then we would prove that by induction. Okay. Just the fact that you have to prove that, something which seems so trivial, might give you an idea as to why the axiom of choice is an axiom. Okay. Let's recall the definition of what a well-ordered set is. Okay. Well, I think this is a little bit fuzzy. Okay, that seems better. I didn't do anything, but somehow it's better. Okay. Let me just remind you of the definition of what it means to be well-ordered. Let A be a set. A is non-empty. A is called well-ordered if there exists a linear order less than or equal to on A. Let me remind you what that means. That means A is less than or equal to A. A is less than or equal to B. B is less than or equal to A implies A equals B. 3. We have a transitivity. And then finally, we have for all A and B, either A is less than or equal to B or B is less than or equal to A. Okay. That is a linear order. And then the set A is called well-ordered if that holds, and every non-empty set has a least element. Okay. And we saw that the fact that every non-empty subset of the natural numbers has a least element, that's like equivalent to induction. It's called the well-ordering principle. Okay. And now we're saying if we have any set which has a linear order such that any subset has a least element, then we call that a well-ordered set. Okay. And now I want to show that now we can now we're going to construct a kind of a choice function for a certain set. Okay, proposition. Let A be a well-ordered set then the power set of A has a choice function. Okay, so this will kind of, I hope, clarify what a choice function is. proof. Okay. So let B be in the power set of A. We need to construct kind of find f of B in B for all B that are non-empty. Okay, so we need to build up a function. If you've been going along with class, building a function is not easy. You don't get it for free. You have to do some work or something. Like, for example, to define the factorial, you can't just do n factorial is n minus 1 factorial times n and put dots. You have to do this thing called the recursion theorem, Okay. So how should we construct this function? Well, we use the property that since A is well ordered, every subset B has the least element. Okay. But A is well ordered. And if B is non-empty and a subset of A, then B has a least element. Say like XB and B, and then just define f of B to be the least element. Okay. And the point here is that the fact that every non-empty subset has a least element allows us to make a choice, because the choice is made for us. A well-ordered set, every subset has a least element. Well, you don't really have to make a choice, just choose the least element. Make that the value of the function. Okay. Since a least element, since being a least element is uniquely defines XB, kind of the choice is taken or is made for you. Okay. So now we have a function. Now F defines a function from the power set of A to all the elements are in B, which is a subset of A, to A. And and we can just define F of the empty set to just be whatever. This can just be anything. This is some element of A or not. Doesn't matter. Okay. So now we have a function from the power set of A to A such that f of B is an element of B if B is not empty. In other words, we have a choice function. Okay. So sometimes the choice can be you don't need an axiom to choose. The choice comes from some property of some special property or something, right? Okay. And the reason I wanted to do this proof was to tell you, well, now if you don't have a way to if you don't have a nice and neat way to choose the element of each subset, that kind of takes away your ability to prove anything about having a function. Okay. Okay. Actually, you can prove a converse to this proposition. You can show that if you have a choice function for the power set of A, then you can define a well ordering on A. Okay, so let's sketch that. Well, this proof is where like transfinite induction would come in. So that it's just going to be a sketch. Oh, is the choice function a bijection? Oh, no, that is a good question. Okay, before I do this next proposition, let's just do another example. Suppose all the elements have like a common element, right? Suppose that X is in A for all elements of X, then you get a choice function for free, you know. Then define f of A equals X for all A in X. Okay. So if there's something in kind of the intersection of all the A's, then you get you get a choice function for free. Okay. So in this case, this function, so f from X is going to just the singleton. This is definitely not a bijection. The value is the same at every subset of X, of every element of X. So this is like the constant function and like the opposite of a bijection. It's not a bijection. You know, and an example where this might happen, you know, well, this is like from algebra, but like so like for example, if X is a set of groups, so every element of X is a group. Now groups will have an identity element because that's one of the definite, like that's one of the axioms for groups. Okay, so then choose. So then you can define for G and X, f of G to just be the identity of G. Okay, this is another example where you kind of get a choice function without having the axiom of choice. Because the identity of a group, that's a thing that is given to you from like the definition of a group. Okay, and if you don't want to, if you're not taking abstract algebra right now, that's okay, just ignore this example. Okay. So the choice function is not really a bijection necessarily. Okay, thank you for that question. Okay, so before that example, I was going to talk about kind of a converse. Let's see. So another proposition. Let A be a set and F from the power set of A to A be a choice function. Then A can be well ordered. Okay. So the sketch of the proof, this is only a sketch as I'll explain, but anyways, the idea is that how do you choose the least element? Well, you look at A as a subset of A. So choose, or we'll put A0 to be F of A. Okay. because we have a function from the power set of A to A. A is a subset of A, so A is an element of the power set. And then so f of A is an element of A. Okay, and what about, then we'll define A1 to just be A, except for the thing we've already chosen. Okay. Now, our choice function allows us to choose an element of A1. By the definition of choice function, this is an element of A1. So in particular, A1 is not equal to A0. Then we just put A2 to be A1 minus A1. Okay. Well, then A2 is just f of A2, which is in A2. Since f of A2 is in A2, A2 is not equal to either A0 or A1. Okay. So at each step, we keep on choosing a different element that we haven't chosen before, and we just keep on going. We choose an element that's not the same as A0, A1, or A2. We choose A3, and we choose A4. We keep on going. Okay. And here would be where transfinite induction would come in. Because, you know, but actually not only transfinite induction, but just because you have transfinite induction, you also have a transfinite recursion theorem, which is what you need. Okay. But anyway, like, so you keep on going, and then if you have an ordinal lambda, which is f of A lambda in A lambda, then you just put A lambda plus 1 equals A lambda minus a little a. And then you choose A lambda plus 1 to be f of A lambda plus 1, which is in A lambda plus 1, and therefore is distinct from all the things that came before it. Okay. And then if you've chosen and then if you have like a lambda which is of the form mu such that mu is less than lambda, and you've chosen a mu for all mu less than lambda, then choose A lambda to just be the elements of A that are not in A mu such that mu is less than lambda. And then choose A sub lambda equals f of A lambda. Okay, this is a very rough thing, but to apply transfinite induction, you need to you need to show that if you have an ordinal given like this, you need to, and you've chosen all the A's for these mu's, you need to show that you can choose it for lambda as well. But anyways, right? And so the point is that eventually you completely enumerate all the elements of A, and that gives you a well ordering for A. Yeah, and that is what happens. Okay, so eventually you write A as like A0, A1, A2. You just put it in increasing order like that. You have A omega plus 1, and you just keep on going forever and ever until you've completely written down all the elements of A, and then that gives you a well ordering for A. Okay. Okay, so when we talk about the axiom of choice, there's actually like 3 things that we can be talking about. Okay. We have the axiom of choice, which says let X be a set, and then naturally whose elements are sets. Then there exists a choice function for X. And then the well ordering principle which says every non-empty set can be well ordered. Okay. The third one is called Zorn's lemma, which I will get to later. But let's take a little bit of time to see that, like, to answer the question, why are these 2 things equivalent? So actually we've seen that if you can so we've seen that, well, kind of as a sketch, but we've seen that if you have if every set has a choice function, then you can well order every set. Okay, so we've seen that the well ordering principle implies the axiom of choice. No, is it the other way around? We've shown the axiom of choice implies a well ordering principle. And well, the reverse is true too. If you can well order every set, then you get the axiom of choice, because again, you have the ability to choose the least element of every set. Okay, and the reverse is true too. Okay. Some other corollaries to the axiom of choice would be if I have a collection of sets then the Cartesian product is non-empty. Okay, because I'm able to choose an element from each xi. Oh, a collection of non-empty sets, of course. Okay, what's another corollary? So this is assuming axiom of choice. Another corollary to the axiom of choice is suppose A and B are sets. Then either the cardinality of A is less than or equal to the cardinality of B, or the cardinality of B is less than or equal to the cardinality of A. So the proof would be the proof is to basically use the well ordering for A and B to find ordinal numbers mu and lambda with the cardinality of A equals mu, cardinality of B equals lambda. And for ordinal numbers, it's true that either mu is less than or equal to lambda or lambda is less than or equal to mu. Okay, so this is, I can't really call this a proof. So, but if you want, the idea is to like go through the proof where we proved that the axiom of choice implies the well ordering principle and like enumerate all the elements of A and enumerate all the elements of B and look at whichever one takes more stuff to enumerate. You know, like eventually, like you'll either have written down all the elements of A first or all the elements of B first, and then that gives you like a one-to-one function from A to B, for example. Okay, so that's very, very rough, but hopefully it's not so bad. Okay, so this tells you why we didn't like this should have been one of the fundamental things about cardinality, and that's why we didn't handle it until now, is because it requires like another axiom that we didn't get to before then. Okay. Okay. So let's take another break until 4:20. I hope that's okay. And we'll continue talking about the axiom of choice for a little bit. Okay, so yeah, see you guys back in 7 minutes.